All right? Can you hear me?
Okay. Our next speaker is Alberto Nocera from Quantum Matter Institute, and he will be talking about performance of device quantum annealer devices.
All right.
Welcome.
Thank you for the introduction, and thank you all for coming. So my name is Alberto Nocera. I'm a staff scientist at the University of British Columbia. My expertise is classical numerical simulation, DMRG, and matrix product state. I know that in the title I put this word, so I should explain. And basically, the explanation is down here. So what we demonstrated is that the latest D-Wave quantum processing unit can work in the coherent regime at a scale which is not possible to simulate classically. And you can find all the details in this 50-plus pages paper on the archive. All right. So this was work done in a big collaboration. The experiments were done at D-Wave, of course. And then the numeric sides involved myself at UBC and people at Oak Ridge National Lab and University of Poland as well, and University of Waterloo, Perimeter and Vector Institute, and also BU. So to be more precise, and if I want to divide this big team by task, as I said before, I'm going to tell you my side of the story on the MPS simulations about this work. But then we also tried more sophisticated tensor network answers like PEPs and also neural network quantum states to simulate the problem. And also we did some critical exponent analysis. All right, so this audience doesn't need an introduction to analog quantum simulators. That was already done yesterday morning. And so what I want to say here is that we have different platforms, and the main advantage is that they can scale up to the number of qubits, and we don't need to worry about fidelity. But the only drawback or problem is that they are special purpose. So either if you are interested in static or dynamical properties, you need to work with a special Hamiltonian. And so my goal is that on this column here, on the side of superconducting qubit simulators, you can add the D-Wave Annealer as an analog quantum simulator. And so let me recap for those of you who are not familiar with the D-Wave quantum computing device. Is a grid of many of the order of thousands superconducting flux qubits, so different from those at Google and IBM. And those qubits are coupled together by tunable couplers. But long story short, this device implements the transverse field Ising model with tunable time-dependent parameters, the exchange interaction of the Ising part and the transverse field. And so as was also already introduced this morning in the very first talk of this morning, the original idea of the design of this machine was to solve an optimization problem by adiabatic quantum annealing. And so this means that if you start from a state where all the spins are aligned in the transverse field direction, and you turn off the transverse field slowly and turn on the Ising coupling slowly again, you're guaranteed by the adiabatic theorem in quantum mechanics that you will end up in the ground state of your final target Hamiltonian, that is this Ising part. However, today, we are not going to use the D-Wave device as a way to optimize any Hamiltonian. We are going to use it as a quantum simulator. And so recently, this was possible because there were some calibration improvements, and in particular, which improved the coherence times of these flux qubits and also the connectivity. Now it's possible to connect each qubit up to 20 neighbors. And then also the synchronization was a key to reach fast annealing speeds, which I'm going to discuss in a few minutes. But here I show you two examples of recent work from the D-Wave group, where they studied the transverse field Ising chain. And they, as discussed also this morning, here they plot the density of things as a function of annealing time. Annealing time for this talk means inverse of the annealing speed. And basically, there is a blue region here where the results of the device follow the coherent regime, which is a power law of the density of kinks as a function of the annealing time. And a similar story was derived in this spin-glass paper last year, where, however, only the quantum critical dynamics and the Kibble-Zurek exponents were basically checked by looking at observables in ensemble averages. And I'm going to be more clear later on in the talk. But the main take-home message here is that now this machine seems to work at large scales of the order of 1,000 qubits and for sufficiently fast annealing times in the coherent regime, and the coherence effects, so deviation from this power law behavior appears on the range of TA, that is this annealing time of the order of 30 nanoseconds, also for slow but not too slow anneals, right? Otherwise, you start to keep to introduce decoherence and noise effects. And so this talk is about doing a quantum simulation of the transverse field Ising model of a spin glass. So the Ising part has couplings Jij here that are random. We consider two cases. One is the case where these couplings are either just plus or minus 1. And the other case is when this J can be any number between minus 1, but doesn't matter, the results are very similar, and we consider different lattice geometry, starting from 2D, and then we consider cubic diamond, and this special almost all-to-all lattice geometry where each row of dimer qubits is coupled to the other row of qubits that it's infinite dimensional. And as I said at the beginning, we solved the coherent, like, closed system Schrödinger equation, assuming that is a valid theoretical framework to solve this annealing problem with MPS, PEPs, and neural network quantum states. So before I go into the results, let me recap. I think many of you are familiar with the concept of bipartite von Neumann entanglement, but let me recap what happens in the case you want to use a matrix product state to approximate some quantum state. So basically, you are fine, and the representation of your quantum state is efficient in terms of an MPS when, for instance, you are interested in ground state of gapped Hamiltonians. And this is called area law in the sense that it has been shown that for area law states, the entanglement entropy doesn't scales with the number of qubits at the edge of your bipartition. In 1D, the edge of a bipartition is a point, so it doesn't scale with the number of qubits or sites. And so MPS representation of quantum states are efficient. So that's why I put a green box here. So your bond dimension that you need to describe your states doesn't scale with the number of qubits. However, if you want to enforce a description of your quantum many-body states in terms of an MPS in 2 or 3 dimensions, you run into problems. And that's why people say, well, the MRG on MPS doesn't work in 2D or 3D. Because in that case, the bond dimension will scale exponentially with the system size. And so people have invented like generalization of MPS to higher dimension, like it's called PEPs. And in this case, you can show that in this case, for instance, the entanglement entropy of a PEPs scales like with the correct area law behavior. So you can describe an area law state with a finite bond dimension in 2D, but you can generalize this in 3D as well. And so this was area law story that I was telling you. It's all about ground states in equilibrium, but now we are doing annealing at a finite speed, which is a process that brings us out of equilibrium. So what do you expect to see in terms of von Neumann bipartite entanglement in this case? So if you do this anneal very, very fast, so your wave function does not have time to react to the change in the parameters of your Hamiltonian, and so the entanglement, the bipartite, the von Neumann entanglement stays low at the end of the anneal. If you do it fast, or if you want slow but not too slow, then you get an area law scaling, but with only logarithmic corrections, because that's given by the fact that you are traversing a quantum critical point. And this is the correlation length that scales, that increase polynomially with the, not polynomially, with TA to the power 1 over mu, where mu is a critical exponent. And so, and this small d here is the dimension. So in one dimension, you expect that the entanglement entropy at most scales logarithmically with the TA, with the annealing time, and that's what was verified about 10 years ago by this group of people, where they show basically that the entanglement entropy is a function of TA, basically goes up and then goes back down, but then the peak for different system sizes scales up logarithmically. So what happens then in 2D or 3D? That's what we did in this paper. And here I'm showing you the entanglement entropy is a function of, this is not annealing time, it's a function of time. So basically from the start to the end of the anneal. And to summarize these two panels, and this is an 8x8 system, square lattice spin glass Hamiltonian, we verified that the largest, actually this was at the beginning of the project, we saw that if TA is between 1 and 20 nanoseconds, we are in the highest, largest entanglement regime, which is actually what the experiments can do. As you can see here, this blue curve goes up. You need to focus at the value of the entanglement at the end. And so, yeah, so basically, yeah, let me show you some results. So we benchmarked at small scales the machine using MPS simulation, and to do that, we computed the correlation metrics, sigma c, sigma z at the end of the anneal. Of course, there are some more, if you want, nice observables, like this q square that is related to the spin glass order parameter, and also the residual energy. But basically, as you can see, these two plots, you have a very good matching, extremely good matching between the QPU results and the MPS, which here, because it's a 6x6, we could perfectly converge it to we could extrapolate the results to infinite bond dimension. And so the reason why that this works at small scales is because the entanglement area law is already an enemy for MPS, but not so an enemy because it's still 6x6. So the key point here that we observed to compare and to, as a metric, right, to judge the quality of the QPU results, we compared QPU and MPS simulation by evaluating this epsilon c, that is this correlation error. Basically, this C and C tilde are the QPU where MPS converge results, where we sampled the order of 1 million times at the end of the anneal. And as you can see, this epsilon c, we observed that this epsilon c doesn't scale with the number of qubits, at least until the point we could classically simulate the system, right? So there is a really flat dependence for most of the lattice structure that we considered, and we confirmed that this is a metric that I like because it's more physically kind of oriented. But we verified this that this kind of behavior happens also using classical fidelity and total variation from the sample for the two sample distribution, the one of the QPU and the one of the MPS. And so the second key point that I want to make is that we could be able to extract an equivalent QPU bond dimension, which means now that we are comparing MPS against himself, basically a converged MPS simulation against an unconverged one at finite bond dimension. And as you can see in this plot, we have this epsilon c versus this chi of the unconverged one, and for different here system sizes in 2D. And we extracted an equivalent bond dimension, as also was done in this recent paper by Andres et al. An equivalent, we matched the QPU error, right? Although I showed you before a very good agreement, if you look closely, there is of the order of a few % deviation between the expectation value of the QPU and the MPS result. So we could extract kind of an indirect measure of the entanglement of this final state at the end of this non-equilibrium annealing process. And so then we try to scale this chi-q, this equivalent bond dimension, as a function of the bipartition area in this different lattice geometry that we studied. And bipartition area is this n d to the -1 over d. And we basically show that the bond dimension scales exponentially with the number of qubits. So the overall story is that this D-wave machine simulates area law states. And so, of course, we extrapolated, assuming that this epsilon c doesn't scale with system size, even beyond what we could classically simulate. We extrapolated what would be the classical resources that you would need to simulate with MPS sizes of the order of hundreds or thousands of qubits. What we could simulate actually in practice, even using supercomputer facilities at Oak Ridge, Frontier, and Summit, actually also, we basically stopped at 64 qubits. Well, it could be 8 by 8 or 3 by 3, like 3 cube basically in 3D. And we simulate very long time dynamics with a good bond dimension, and we use to evolve in time the MPS simulation. For those of you that are curious, we use the time-dependent variational principle, which I'm not going to talk about because it's technical. And so, yeah, so basically, in summary, so it seems like this D-wave QPU can reach can describe the situation beyond what is possible with MPS simulation above dimension 1. But this is not the end of the story. What about the other two techniques that I told you about at the beginning, PEPS and neural net? I don't have time to dwell into those, and I can summarize this in a sentence. There are problems in both, and they cannot even compete with the MPS simulation in 2D, to our surprise, actually, to my surprise as well. Because, as I said before, in terms of the entanglement, the problem of PEPS, for instance, is not just the bond dimension, but is the size of the neighborhood. There is a contraction complexity that is exponential in PEPS to compute expectation values. So you need to truncate to some tensor neighborhood update that you need to do to compute expectation value. And the Kibble-Zurek physics tells you that this correlation length increases with annealing time. So if you go to times long enough, you need to increase the size of the neighborhood, and that puts PEPS, for instance, into trouble. So basically, all the classical methods we tried failed. And again, we described a single instance of disorder, right? So of course, we consider random couplings, and all these methods were tried for a single instance of disorder, not average ensembles. So, and then, yeah, so what about some physical intuition about the problem? Can we exploit locality? I told you about this finite correlation length. The answer is you can exploit locality in this problem. And basically, we were able to show in the paper that if you can simulate classically a cluster big enough of the order at least a few times bigger than the correlation length that is given by the Kibble-Zurek scaling, you can basically you can recover 2D results up to a very large scale, like up to hundreds of qubits, even classically. And we use this traveling cluster approximation, either using MPS as a solver or the QPU itself as a solver. And I don't have time to go into the details of this. So the last, as I mentioned before we verified the machine, that the machine is working beyond what could simulate classically, because ensemble averages of Binder cumulants, they should respect a scaling according to the Kibble-Zurek mechanism. Overall, after all, you are crossing a critical point, and basically we verified that the Kibble-Zurek exponents of there is another bracket here, so the Binder cumulant, ensemble average Binder cumulant scales with TA and the system size in agreement with what you expect from the Kibble-Zurek mechanisms. And yeah, and here I can stop it and just flash the key take-home messages of this talk. Thank you for your attention.
Thank you very much for the talk. We have time for one brief question. So if...
Sorry, maybe I wasn't following your talk too carefully. So in the end, did you sort of prove quantum advantage in this case or not? I'm a little bit confused. What is the message?
We try all our best, yes.
Say it again?
We try all our best. So we tried all the possible methods we could try, and we...
And what is the conclusion? That's what my...
Yeah, we couldn't reproduce the QPU results with the same level of accuracy.
Mm-hmm. Okay, thanks.
Let's thank our speaker again.